The power of finite element analysis, FEA, in structural engineering. Welcome back to Blueprint to Reality. In today's video, we are diving into one of the most powerful tools in modern structural engineering, finite element analysis, FEA. FEA is a numerical method used to predict how structures will behave under various loads, providing engineers with valuable insights into the performance of materials and designs. Whether designing bridges, buildings, or aerospace components, FEA has revolutionized how engineers approach structural challenges and ensure safety, efficiency, and cost-effectiveness in their designs. What is finite element analysis, FEA? At its core, finite element analysis, FEA, involves breaking down a complex structure into smaller, simpler parts called elements. Each element is analyzed individually, and the behavior of these elements is studied under different conditions, such as loads, temperature changes, or vibration. By using this method, engineers can model intricate details of structures and simulate real-world behavior. These individual elements are connected at nodes, and FEA calculates the responses of each node, ultimately determining how the entire structure will perform. This process allows engineers to analyze the entire system without physical testing, saving time and resources. Why is FEA important in structural engineering? FEA is critical in structural engineering because it enables engineers to predict how materials and structures will behave under various loading conditions without relying on expensive and time-consuming physical prototypes. It provides an in-depth understanding of stress, strain, deformation, and displacement within the structure. FEA helps engineers identify weak points in a design, optimize material usage, and ensure that safety factors are met before construction begins. Whether designing a high-rise building, a bridge, or even complex aerospace structures, FEA enables engineers to simulate real-world conditions and ensure that their designs can withstand extreme forces such as wind, seismic activity, or heavy loads. Types of FEA analysis. FEA can be used for different types of analyses, each tailored to the specific needs of the project. For instance, static analysis is used to determine how a structure will respond to constant loads, like the weight of the building or a bridge. Dynamic analysis, on the other hand, looks at how a structure reacts to time-varying forces, such as earthquakes or wind gusts. Thermal analysis assesses how temperature changes affect the material properties and overall performance of a structure, while vibration analysis is crucial for identifying resonant frequencies that could cause dangerous oscillations. These analyses provide engineers with a full spectrum of information, allowing them to design safer and more efficient structures. How FEA improves structural design. One of the most powerful aspects of FEA is its ability to test multiple design scenarios without the need for physical prototypes. This capability enables engineers to experiment with different materials, geometries, and load conditions. Engineers can modify their designs and quickly see how changes affect the performance of the structure. For instance, if a specific section of a building is found to be under excessive stress, FEA can help identify the exact area of concern, and modifications can be made in real time. This flexibility allows for better optimization of materials and design, ultimately leading to cost-effective solutions and higher quality structures. FEA in complex structures. When it comes to complex and innovative structures, FEA becomes even more invaluable. Modern architecture and engineering projects often involve non-standard shapes, composite materials, or advanced construction techniques that are difficult to evaluate using traditional methods. FEA allows engineers to model these complex systems, including intricate curved surfaces or multi-material assemblies, with high precision. In aerospace engineering, for example, FEA is essential for analyzing the performance of aircraft wings or fuselages under various aerodynamic loads. Similarly, in civil engineering, FEA helps with the design of complex high-rise buildings, suspension bridges, or tunnels.